Let's meet some of the models. Think of this portion of the lecture as your chance to get to know more about some of the transition metals and figure out their chemical personality and find your favorite. So here are some of the transition metals of period 4, what a lot of our examples will focus on, but they're not going to be the only transition metals that are important, okay? These elements are in the same period, so they're bound to have some kind of similar characteristics, but for now, let's just learn a bit about each. First on this catwalk is going to be scandium. So scandium is actually named from the Latin word Scandinavia, and is found in the Earth's crust, so it's actually very rare. It's going to exist mainly at the +3 oxidation state. It's actually a soft silvery metal like we see here, but in compounds, you'll see it as white, okay? And the reason why is because scandium compounds normally are going to have filled d orbitals. When you have filled d orbitals, a lot of times you're going to see white compounds, and when you don't have filled d orbitals for these transition metals, you'll see color compounds. And of course, we'll talk about that further as we go along. Next up is the hard, strong, silvery metal that is titanium, okay? And it definitely has its name derived from the Titans of Greek mythology. So it actually has a low density, high strength. It's used in jet engines to make the pipes and pumps and reaction vessels, and it's found in a lot of different cosmetics, I would say, as well, okay? Now, one cool thing about titanium and a lot of other transition metals as we go along, especially in period 4, and a lot of them as well outside of period 4, is that they can have different colors based on their oxidation number. So here we're going to have titanium 4. So this is going to be titanium with +4 oxidation number. But if you were to have titanium with the 3+ oxidation number, you actually can form a compound with it that is going to be purple, for example. And we'll be seeing that as we go along. Next up is vanadium. Okay, it's a soft, ductile, silvery, light metal, as we can see here. Okay. It's going to be named after the Scandinavian goddess, Vanadis. Or for us, I always remember Freya from Norse mythology. Again, it's going to be named because of the variety of colors of salt that it forms. A lot of times you'll see vanadium mixed with a lot of metals for like jet engine parts, ceramics, glass, etc. A lot of the principal oxidation state, meaning the most stable compounds that it forms, is going to be when vanadium is going to be at +5. It's very hard and corrosion resistant. So you want to have these kind of vanadium elements, a portion of it, so that you can always keep your metals and your metal compounds up. Okay, folks? Now, vanadium can have different oxidation states that give different colors. So, for example, instead of this blue compound that we see here, if you have vanadium 2+, you could have a violet compound, for example. All right, and next up, we're going to have good old chromium. Now, chromium is also a rare element. It's going to be important in industrial materials. The name is derived from the Greek word color, which is chroma. Again, because of the wide variety of colorful salts that it produces. So we see one of the colors yellow here. And because of the varying oxidation states, you can have different colors. So when you have chromium 3+, chromium +3, that is going to be in aqueous solution, you actually can get the color green, for example. And again, when it comes to chromium, it's usually going to be hard and brittle, and it's going to have compounds that are stable when you have chromium +2, +3, or +6. Next up is manganese, okay? It's going to be a hard gray-white metal, which is very brittle, and it's pretty reactive because it's going to exist in all oxidation states from +2 all the way to +7. That means it also can have various colors as well. So here we have more of a white compound, but we also can have manganese +7, which can produce purple compounds, for example. They're going to be used for anything that has manganese in it. Is going to be used for producing hard steel, which can be used for rock crushers and armor plates. And when you're thinking of manganese, you're also thinking of the Latin word for magnet. So manganese is going to be the Latin word for magnet. Since these manganese compounds can actually form different types of magnets as well. You can also use them for like coloring agents, for paints and ink. And one cool thing about it, which we'll see with other transition metals, some of them can be dietary supplements. So if you take manganese, it's going to be good for like your bone health, for example. Now on to one of our most abundant models, right? Our iron transition metal, which is going to be the most abundant heavy metals, appears white and lustrous. We do see the forms here of iron that's going to be like that brownish color. It definitely has formed already some oxides on it. It's very highly reactive, okay? And it's always going to have the oxidation states of +2 and +3. That's where the chemistry of the iron is really going to come from, okay? So as you can see, it does have different colors that can form. We have this like reddish color here, but you also can have like iron 2+ in some compounds that can form our really like a brownish black color as well. And as we're going through the transition metals and talking about some of these compounds, the cool thing is in lab, we'll be able to recognize a lot of these transition metals and the compounds they form as we go along and see all the labels on the chemicals. Okay? Now, when we're thinking of the name, is going to come from the Anglo-Saxon word metal or iron. Okay? And so it also can come from the Latin word ferrum. So sometimes you'll see like when you're naming metals in general, and we've got to iron or naming like transition metals, it always have to have those oxidation states. So when I was talking about transition metals as well, remember, we do have to have the oxidation state in those parentheses for all the different names. That's why oxidation states are important. And we know iron is so ubiquitous, right? Structural steel, automotive parts, nails, machinery. And of course, like we were saying before, oxygen transport in our blood. So literally it's transporting oxygen to our brain, for example, all through our blood and circulation. That's probably one of the most important portions of iron to the human experience. What's next is going to be our cobalt, another rare element that's going to appear our bluish white, okay? So of course it is kind of hard to see all the perfect, like illustrious portions of the metals. You will have to get better pictures for that, but of course I am kind of showing you what it looks like as an element and in compound form, as many as we go through all the examples for period 4, okay? So for cobalt, just know that it's used in a lot of alloys, and alloy is going to be a mixture of metals. So it's used in stainless steel, which is a mixture of metals. It always is going to have more stable compounds when it has a +2 or +3 oxidation state. And it's actually named for the German word for goblin. So the German word for goblin is Kobold. So because of like basically a bunch of miners went in and they started to try to get cobalt or silver from all these different mines. And they ended up heating up this ore that had cobalt in it, and it actually ended up having so much different types of horrible fumes, and that's why it got kind of like that goblin name, okay? Now, cobalt is going to be used for a variety of things, but it's definitely a chemical reaction catalyst, meaning it can't be used up in a reaction, but you can use it over and over and over to make reactions faster. Also, they're an orthopedic implant, which is pretty cool. And one of the coolest parts, of course, is that it's a component of vitamin B12. So that's going to be helping with energy, metabolism, and of course, nervous system function. Now, when we get into nickel, over here, we see that it does have a green compound as well, but it's a silvery white metal when it's its own element, okay? It has high electrical and thermal conductivity, resistance to corrosion, like we see with a lot of these transition metals, right? And the +2 oxidation state is going to be the most stable for it. Now, the name is actually derived from the fact that people used to basically try to use nickel as a form of copper, okay, or false copper. And so it was given like this, another German term, Kupfernickel, which means like old Nick's copper or something like that. And I just remember it being like, okay, old Nick's copper is like a false copper, a fake copper. And so because nickel was mistaken for it, that's kind of how it got its name. And so a lot of these are going to be found in ores that have a lot of mixtures of other types of metals as well. You can use this nickel for coinage, obviously, musical instruments like saxophones, batteries, and coating of surfaces because it's so resistant to corrosion. So it's just a lot of different options for it. And of course, both cobalt and nickel can have different colors. So we have this cobalt here, but we know if I have cobalt +3, I can actually have a yellow color instead of the reddish color I see here. And then if I had nickel +2, I actually can get a yellow or blue color instead of the green we see here. So the fact that we can have a lot of different color compounds definitely helps us as well when it comes to industry, being able to isolate some of these compounds as well, and for identifications of things that you actually have in solution, for example. And we're down to our last two models of the period 4 transition metals, copper and zinc. So let's start with copper, the most widely abundant one that we ever see in natural ores, okay? So that means you'll see copper in a lot of different ores or those rocks that actually have different transition metals and minerals within it. So because of that, you can actually see copper being separated in a lot of different ores as well when you want to use it for other things. High electrical and conductivity, and it's resistant, very resistant to corrosion. Likes to form stable compounds with copper +2 oxidation state, okay? And it got its name from the Old English name copper, which is in turn comes from Latin word cuprum, because it came from the fact that it comes from the island of Cyprus. And back in those times, it was the Mediterranean area that actually was the leading supplier of copper. So when it comes to language, the Latin word was just like, okay, Cyprus. And then, of course, the English turned into copper. So that's when they got that, okay? Copper is very malleable, ductile, and it's usually going to be this reddish brown metal that we normally see here. Obviously, we can see it in different compounds as well. And because we have that color, it's basically telling you that copper can also have multiple colors of different oxidation states. So if we have like copper +2 oxidation state here, we can actually get a black color, a blue color, or green color, depending on what it's attached to. Okay? So there's a couple other things about it. Oh, we use it for like electrical wiring, coins, like penny, bronze sculptures, electronics, roofing, gutters. And we use it for so many different things, especially with the structural portions, like electrical wiring. Okay, folks? But it definitely can corrode when exposed to air. So a lot of times you will see different platings on top of it as well. So it can basically try to keep the copper as long as possible. One cool thing is also we talked about alloys, which are mixtures of metals. And you do see a lot of copper that's going to be in brass or sterling silver, even 18 karat gold. Okay. So now let's get into zinc, our last period for transition metal. It's very white and lustrous, okay? It's highly active metal. It's used for galvanizing steel, which means that it's providing a layer of protection for coating because it's it's not as corrosive, right? So for example, the copper that I already know is going to corrode, if it was galvanized with zinc on top of it, for example, then it won't corrode as fast because the zinc is going to protect it. You see what I'm saying? Also, zinc is going to form colorless salts, and normally the +2 oxidation state. So that means that zinc, you won't see it in a lot of different colors. You actually have a full electrons filled in all the d orbitals, so it normally is going to have a lot of basically colorless types of compounds. Okay? Zinc on its own, though, does have that white and lustrous kind of view to it. Now, the name is derived from the German word for the metal, which is zinc, right? But it also could be in turn related to the Persian word for stone, which is also zinc. Okay, and so you see zinc in a lot of sunscreens, fertilizers, batteries, again, coatings for steel or different types of other transition metals because it definitely is resistant to corrosion. Okay, also zinc is another dietary essential. You can take zinc and use it for enzymes, which help speed up chemical reactions in the body, immune support, and wound healing. So a lot of options when it comes to all these different period 4 transition metals. All of them are not going to be something we focus on, but you will be able to see a lot of them as we're going through this entire journey of chapter 19. That's why it's always good to try to get little details of them to help you remember small little amounts if you can. So if you do see any of these period 4 transition metals in your compound, fear not, always stop yourself and just try to remember tiny little things about them just to help you not basically decrease anxiety when you see them. Okay, folks? Now let's go ahead and talk about some things that are not the period 4 transition means.